Hi everyone, I am Dr. Surjit Singh. Today we'll talk about the Leetcode problem evaluate division. The second method will use union and find data structure. I am excited to talk about this. Let us begin. We are given a list of pairs of variables and the values of their ratios. None of the ratios is 0. We are to find the ratio of another list of queries. We will set up a graph and use it to search the required ratio by following DFS approach. We are given two pairs and their ratios. It means that A by B is 2 and B by C is 3. Queries are A by C, B by A by E, A by A, and X by X, for which we will find the values. We define a graph as a default dictionary defined in collections. The values in the dictionary will be dictionaries too. We use input to set up the graph. In the first iteration, we save A by B equal to 2. A is entered as a key in graph. Its value is also a dictionary in which B is the key and 2 is the value. We make another entry in graph against B in which A is the key and 0.5 is the value, since B by A is the inverse of A by B. In the next iteration, the pair BC is processed. B by C is saved as another entry against B, while C by B is saved as an entry in C. Each variable can be considered as a node in the graph. For n equations, there are two n edges in the graph with different weights. A to B edge has weight 2, while B to A edge has weight 0.5. We will require DFS function in order to handle the queries. Our aim is to find a path from dividend to divisor. We create a list to hold results of the queries. We consider the first query in which we want to find A by C. If either of them is not in the graph, the result is -1 to indicate error, while if both of them are same, result is 1. Otherwise, we call the recursive DFS function to compute the results. Initial value of product is 1 while the visited set is empty. We add A to visited and initialize return value as -1. DFS is called recursively, so we will remove the current node from the set at the end of each DFS call before returning the result. Neighbor of A is dictionary B2. If target is present in neighbors, our problem is solved. But C is not present in neighbors, so we process all neighbors of A. The loop will run once as A has a single neighbor B with val equal to 2. We ensure that neighbor is not already visited, otherwise the search process could become endless. We make another call to DFS from neighbor to target. Note that target remains same in every call. Product times val becomes the product in the new call. We add B to visited and initialize the return value as -1. We look for neighbors of B and notice that target is present there. Logically, it means that A to C can be achieved as A to B and B to C. It also means that A by C is same thing as A by B into B by C, which is 2 into 3, that is 6. Return becomes prod times value of neighbor, which is 6. It is important to note that the set visited is exchanged between all calls of DFS. So before returning the result to the previous call, set has to be restored to its original form, so we remove B from it. Returned value from the previous call is 6. As this is no longer equal to -1, the problem has been solved. We break the for loop and return 6 to main function and append it to the results. In the next query, we evaluate b by a. Both are present in graph and they are not same, so we call DFS. B is added to visited and ret is -1. Neighbors of B have A present in them, so ret becomes 0.5 and we save it in results. Next is A by E. As E is not present in graph, we directly save -1 in results. Note that A by A is directly saved as 1, while X by X is -1. Finally, we return results to the main function. Each equation gives two entries in building of graph, so n equations take O(n) time. For each query, we may visit at most all the n nodes. For every query, time complexity is of the order of n, so for m queries, time taken is mn. There are 2n edges in the graph, so space complexity is of the order of n. Maximum depth of the call stack is also n. We will use the union and find data structure in this method. In this, we divide the data into disjoint sets or groups. Git weight is used to set up the graph. We will gradually develop two functions, union and find. Find gives us the group to which an element belongs. Union merges the groups which form a chain and are in the same group. In the first iteration, we call union function on the first equation that represents a by b equal to 2. This function further calls find a. Element a becomes the node ID in find. It is not present in git weight, so we save the default tuple that is node ID 1 in git weight against node a, which means group ID is A and node weight is 1, which is the value of A by A. Group ID and node ID are same, so we skip the if statement and return A1 that are saved as dividend git and dividend weight in union function. Next, we repeat the process on divisor, that is B. It creates another entry in git weight and the tuple b1 is returned to union as divisor git and divisor weight. Now, dividend git and divisor git are not same. However, they should be in the same group because they are related to each other by an equation. So we merge the two groups together by changing the entry against dividend value A. That is, we change its group ID to B. Its new weight becomes val times the ratio of old weights. The git weight now shows that both A and B belong to same group B and A by B is 2 while B by B is 1. Next, we repeat the process for the second equation B by C equal to 3. First statement of union function calls find B. We note that B is already present in git weight, so we don't make a new entry but retrieve the old entry, that is B and 1. Group ID is same as node ID, so we return B1 and save them as dividend git and dividend weight. For divisor, we perform find C. It is not present in git weight, so we initialize them with default values and add them as a new entry in git weight and return them to union function. We notice that dividend git is not same as divisor git, so group ID for B in git weight is changed to C3. With this, the graph has been set up and job of union function is over. We can read the table as A by B is 2, B by C is 3, and C by C is 1. We don't need the union function anymore. We now consider the list of queries. The only query we consider at the moment is A by C. We define a list to store the query results. In the query, dividend and divisor are A and C. Both A and C are present in GID so we call find A, for which group ID is B and node weight is 2. Group ID is not same as node ID, so we call find B, for which group ID is C and node weight is 3. Again, group ID and node ID are not same, we call find C. This time group ID and node IDs are same, so this returns C1 that are saved in the previous call as new group ID and group weight. Git weight B becomes C3. Actually, it remains unchanged because group weight is 1. C3 is returned to previous call and stored in new group ID and group weight. So git weight for A becomes C6, that is the product of 2 into 3. Note that every find will change its group ID to its final value, which will be time saving in subsequent finds of the same node. C6 is now returned to the main program and saved as dividend gid and dividend weight. We repeat it with divisor. This time the response will be immediate because all group IDs are same. C1 is returned to the main program and saved as divisor gid and divisor weight. Group IDs are same, so for the if statement else part is executed and ratio of the weights of dividend and divisor is the result and is appended to results. As group ID is same for all the three, all subsequent queries involving these three will be evaluated directly in a constant time. If the two IDs belong to different groups, result is -1, indicating failure in evaluation. If we consider another equation, AA by BC2 equal to 47.2, its entries in gid weight and the result of the query are as shown. We may note that the query B by BC2 is undefined because they belong to different groups and -1 is appended to result. Finally, results is sent to the main program. For n equations, time complexity is n log n. For m queries, each is evaluated in log n time. However, subsequent queries involving old variables are evaluated in constant time. Each variable storage takes constant memory, so n equations take 2n memories. Find operation callback can at most be of size n. So overall space complexity is of the order of n. Thank you for your time. I hope you enjoyed the video. Please stay tuned for more such interesting solutions.